Hello everyone, my name is Eduardo and today I'm going to present you my final project for wireless communication class, MIMO Channel Performance Analysis for 5G and beyond technologies. This is the agenda for our presentation. So I'm going to go over the introduction, related work that we use for this project, the method description, performance evaluation, conclusion, and future work. So for the introduction, today there's a demand for higher data rates, data redundancy, and time critical response or latency. Today we have the 3GPP 5G new radio technology that is used for commercial deployment for smartphones and other IoT devices. And we also have the upcoming 3GPP release 20 that is being studied for the 6G technology, and the usage of millimeter wave and terahertz waves are being considered, so we can achieve higher data rates and also latency response. But the problem is that we will have new challenges and problems, because since we go over the higher frequency spectrum, the signal range is shorter and sensitive, and the system design must be complex, since antennas elements must be smaller and power limited. So to solve this problem, massive MIMO was introduced to address this issue, where an array of antenna elements, usually with 256 or more antenna elements between the transmission and reception, are considered for study and widely used in 5G systems. Here we have an illustration of a MIMO system to give you a background of what is MIMO. So basically MIMO means multiple input and multiple output. It's a common used wireless technique where you can achieve bigger data rates by sending multiple code words on each antenna, or you can have data redundancy by sending the same code word on different antenna elements. So in this illustration here, we have a system with two blocks. So you have the transmitter antenna array, where you have n number of transmission antennas, and you have the channel represented by H, which is the matrix represented by this equation, and you also have the receiving signal, which is represented by Y, where it's composed of the receiving antenna elements going up to M. So after you receive the signal, you also have some noise, usually thermal noise, from the receiving entity. So we can represent MIMO by this illustration and using the equation where Y, which is the received signal, equals the channel coefficient matrix represented by H, times X, which is the transmitted signal, plus a vector of noise, which we introduce thermal noise. Regarding the related work for this project, we use massive MIMO literature from Emil et al. Work regarding the monography book that was used as a foundation for this project to understand core concepts and performance trade-offs, such as spectral efficiency and redundancy for MIMO systems. For our main application for this project, using the new scene software, we have used Rappaport et al. Work, where they have developed a simulation tool using MATLAB that generates channels for 5G research using Monte Carlo simulation. The tool was initially applied to millimeter waves up to 100 GHz, but was now extended to sub-terahertz to a maximum of 150 GHz for indoor hotspot scenario for 6G research. So giving more details about this tool and how the calculation is done, we have some formulas here. So the first equation we have here is the path loss model in closed-in free space that is represented by this function. So basically the path loss model has two parameters. The first one is the frequency, which is represented in gigahertz. The second one is the distance. So this is the distance between the transmitter and the receiving antenna, and we also call this the TR distance. And the other terms for the equation is the FSPL, which basically is denoted as the free space path loss at a specific TR separation. In this case, it's 1 meter. We also have the path loss exponent, or PLA. The AT is represented as the attenuation term from the atmosphere effects for the specific environment that you're testing. And we also have another Gaussian random variable with specific standard deviation for closed-in loop for this equation. And the distance between the TR must be at least 1 meter or above. And then we have the two supporting equations here, which is the calculation for the FSPL, which you basically need the frequency and the speed of light represented by c, and the AT equation as well, where is the same terms that we discussed. Another formula that is used on the new scene software is obtaining the channel coefficient equation. So here we have the channel coefficient equation, which is described for each corresponding antenna element combination of M and K respectively for a specific subcarrier at a specific frequency that is used for a MIMO system. So in this equation we have multiple terms. So the most important term here is the frequency, that is in gigahertz scale. We also have the alpha, that is described as the amplitude of the channel gain. We have the resolvable multipath, the phase of the multipath, tau represented as the computed time delay, the dr and dt, which is the TR separation distance in meters, the azimuth angle of departure, and the angle of arrival respectively. So this will give us the channel coefficients that we discussed on the introduction block diagram example. So here we have other related works that utilize the new scene tool to do channel analyze. So the first work is from Shamsan et al., where they developed an analyze based on a 4x4 and massive MIMO of 64 by 64 on 73 gigahertz frequency on an urban microcell scenario. Another work developed by Hassan et al. Is channel analyze for 28 gigahertz, 38 gigahertz, 60 gigahertz, and 73 gigahertz on 800 megahertz bandwidth on a microcell scenario as well. So this was mainly focused on the millimeter waves, both works on the millimeter waves. And finally, I also looked at Sharik et al. Work, where they did a channel analyze based on 6 gigahertz, 28 gigahertz, and 60 gigahertz under the same scenario from the previous works by varying the distance from 10 meters to 300 meters using a 2x2 system. So in this case, they also did not just compare millimeter wave frequencies, but they also included sub-6 gigahertz frequency, which I will explore in this work as well. In this project, the comparison between a 4x4 MIMO and 256 by 256 massive MIMO performance and the different carrier channel frequencies from sub-6 with 3.6 GHz millimeter wave with 26 GHz and sub-terahertz with 140 GHz under an indoor hotspot scenario, including a line of sight and non-line of sight scenario, are simulated and evaluated. So we have used the new scene channel simulator to obtain the channel coefficients, path loss, receive power, and delay spread at a fixed TR separation. So I'm going to describe the new scene tool that we have used. So here we have a picture of the graphical user interface of new scene. So the new scene uses a statistical model of Monte Carlo to generate a simulated channel based on input channel characteristics and MIMO antenna properties. So as you can see here, there are several options here. For our simulations, we didn't use the spatial consistency parameters and the image blockage parameters. We just used the channel parameters and antenna properties, where our main goal was to use the indoor hotspot scenario for our simulations. So this is a table summarizing the simulation parameters that we have used. So basically all the simulations that were done use the same TX and RX separation distance of 50 meters. The polarization was the copolarization. Array type was the same, using the uniform linear array. TX and RX antenna spacing was 0.5 meters with the exact elevation and azimuth angle fixed at 10 degrees and 10.5 degrees respectively, to have a 24.4 dBi gain on the indoor hotspot scenario. The simulations for MIMO consist of 4x4 antenna elements and the massive MIMO 256 by 256 antenna elements. Sub-6 simulation used the RF carrier bandwidth of 100 MHz, while the millimeter wave and sub-terahertz simulation used the RF carrier bandwidth of 800 MHz. So the reason we used 100 MHz for sub-6 is that it's currently being used in 5G commercial deployment, and the 800 MHz is more practical to millimeter wave and sub-terahertz. So we use a total of 12 simulations divided by 4 for each frequency, and a MIMO and massive MIMO performance comparison under a line of sight and non-line of sight scenario was simulated and analyzed as well. So for our first simulation regarding the sub-6 line of sight comparison between MIMO and massive MIMO, we generated a plot. So we have the omnidirectional and directional path loss as a function of the TR separation and small scale PDP plot comparing MIMO and massive MIMO. So as you can see here, the MIMO directional and omnidirectional path loss converges in the first graph, while the massive MIMO diverges with a small offset. The massive MIMO had slightly more directed gain due to channel coefficient. So if you look at the scalar values that we have here on the legend of the plot, we have the channel coefficient. So for omnidirectional, for example, we have 1.7 for massive MIMO, and for MIMO we have 1.8. So since we have a reduced channel coefficient, this gives us more gain. Right, for the directivity we also have 1.5 and MIMO is 1.6, and the best directivity we also have 1.5 compared to 1.6, so we have some gains here. And the delay spread, which is represented on the small scale PDP plot, is similar between the MIMO and massive MIMO. For the PDP evaluation, on a fixed distance of 50 meters that we have used for our simulations on this project. On the line of sight scenario, for this case, we can observe that there is a reduced path loss and increased received power gain in massive MIMO when compared to MIMO. MIMO and massive MIMO had similar average RMS delay spread. So if you look at the values from the plot, we have the path loss of massive MIMO as 69.6 dBm and MIMO is 71.5 dBm. Receiving power here is 9.2 dBm, and for MIMO is 7.3 dBm, so we have some gains between those two. And for the average RMS delay spread, we can see that they're all 0 nanoseconds here, so they're pretty much the same. For the non-line of sight scenario, we also did the same exercise from the previous discussion, and As you can see from the plots, the MIMO and massive MIMO directional and omnidirectional receive power and path loss is now diverging in both the scenarios. So you can see that the plot is not converging as we saw earlier. The massive MIMO did not perform well in terms of channel coefficient, but for the only for the omnidirectional mode. But there was a slightly better performance in the directivity path. Massive MIMO delay spread from channel was more impacted than MIMO as well, since you can see here the propagation time delay went to 400 milliseconds and for the MIMO up to 350. For the PDP evaluation on the fixed 50 meters TR separation, there's a slight reduced path loss and increased receive power gain in massive MIMO when compared to MIMO. Massive MIMO had slightly better RMS delay spread in the channel when compared to MIMO. So if you look at the values here, you can see that massive MIMO had 29.9 nanoseconds and MIMO had 33.1 nanoseconds for the directional. And for the directional, there's also slightly loss in massive MIMO 0.2 nanoseconds to 0.1. So for omnidirectional case, there's some gain, but for directional, there's some difference. So this is the table summarizing all the simulations we've done for the sub-6. And as you can see here, there's a delta between the line of sight scenario MIMO and massive MIMO, and another column here with the delta between the MIMO and massive MIMO on non-line of sight scenario. So in the line of sight scenario, there is a gain of up to max of 11.52% in receive power and 1.35% in path loss, while the average RMS delay spread was slightly better in massive MIMO. In non-line of sight scenario, there is a gain of up to max of 6.34% in receive power and 1.56% in path loss, but there's a degradation of minus 3.57% in omnidirectional path loss, while omnidirectional RMS delay spread is also impacted. For the millimeter wave line of sight scenario on the 28 GHz frequency with a carrier bandwidth of 800 MHz, we can observe that MIMO and massive MIMO directional and omnidirectional receive power and path loss diverges. Massive MIMO had better omnidirectional and directional gains, and there was a similar delay spread between MIMO and massive MIMO. For the PDP evaluation on line of sight with a fixed 50 meters TR separation, we can observe there's a slight reduced path loss and increased receive power gain in massive MIMO omnidirectional and directional when compared to MIMO. Massive MIMO had more spread delay in the channel when compared to MIMO. And for the non-line of sight scenario, we can observe that the MIMO and massive MIMO directional and omnidirectional receive power and path loss diverges. The massive MIMO had a lower channel coefficient value on the best directional path and omnidirectional path causing lower path loss. The delay spread in massive MIMO is drastically impacted when compared to MIMO. For the PDP evaluation on non-line of sight, there is also a slight reduced path loss and increased receive power gain in massive MIMO when compared to MIMO. Massive MIMO had more average RMS delay spread in the channel when compared to MIMO. And this is the table summarizing our results. So as you can see here, in the line of sight scenario, there is a gain of up to a max of 12.14% in receive power and 1.28% in path loss, while the RMS delay spread was impacted. In the non-line of sight scenario, there is a gain of up to max of 6.29% in receive power and 2.80% in path loss, while the RMS delay spread is impacted on the omnidirectional setup. For the sub-terahertz line of sight scenario, we can see that the MIMO directional and omnidirectional receive power and path loss converges, while the massive MIMO slightly diverges. It is also observed that there is better omnidirectional gain to the reduced channel coefficient for massive MIMO, but similar directional gain when compared to MIMO. Massive MIMO has slightly more delay spread from channel, as you can see from below plots here. For the PDP evaluation, you can see that we have a reduced path loss and increased received power gain in massive MIMO when compared to MIMO, especially on the omnidirectional scenario. The average RMS delay spread is more impacted in massive MIMO when compared to MIMO. For the non-line of sight scenario, MIMO and massive MIMO directional and omnidirectional receive power and path loss diverges. Massive MIMO has better gains due to reduced channel coefficient in omnidirectional and directional mode, and the delay spread is drastically impacted in massive MIMO when compared to MIMO. For the PDP evaluation on non-line of sight scenario, there is a considerable reduced path loss and increased received power gain in massive MIMO when compared to MIMO, and massive MIMO has more delay spread in the channel when compared to MIMO. This is the summary of the sub-terahertz evaluation that we did for the 4 simulations. So as you can see here, for line of sight scenario, there's a gain of up to max of 1.28% in received power and 0.51% in path loss, while the RMS delay spread is impacted. In non-line of sight scenario, there is a better gain of up to 11.65% in receive power and 4.52% path loss power, while the RMS delay spread is impacted in directional and omnidirectional modes. So this is the summary table of all the frequencies where we have the delta between the line of sight and non-line of sight for each frequency. So as you can see here, the simulations results indicate that massive MIMO offers path loss reduction and increased gain in received power for millimeter waves and sub-terahertz frequencies when compared to the MIMO, with some limitations on sub-6 frequency where it was observed path loss in omnidirectional case. The RMS delay spread is constantly higher in massive MIMO when compared to MIMO, especially for sub-terahertz and millimeter wave frequencies. To conclude this project, we utilized the USIN tool to generate carrier frequencies channel for sub-6 millimeter wave and sub-terahertz using Monte Carlo simulation, and analyze each generated channel key performance indicators between the MIMO and massive MIMO under line of sight and non-line of sight scenario. It was concluded that massive MIMO had a good path loss reduction and increased received power gains in millimeter wave and sub-terahertz when compared to sub-6. Such gains can increase coverage and channel capacity due to an increased SNR, but there's a drawback, because since you increase the delay spread, right, because we have observed more delay spread in massive MIMO, we will require more complexity on the system, on the receiving side, where we have to deal with intersymbolic interference. With increased receiving power and path loss, the reduction, it's possible to increase the data rate, because we can utilize higher modulation and coding schemes, and also more number of layers and code words to increase our data rate. For future work, we propose use existing channel coefficients from USIN and apply it into off-DM or NOMA simulations to verify what is the exact channel capacity and the projected throughput rate and bit error rate performance. Also, another suggestion is to verify the channel performance under cell edge scenarios, UMI scenario, as this experiment was only focused on an indoor scenario. So the new sim has a limitation where you are just simulating on an indoor scenario, which is up to 150 gigahertz. And if you want to do a UMI scenario, you will be capped to 100 gigahertz. So in the future, if we can have a way to try the same experiment it would be good for evaluation. This is the reference from our work. And now I'm going to demonstrate the usage of the new scene. So this is the graphical user interface of the new scene. The first thing you need to do is click on Start, and then you need to specify where you want to save and also what are the output files. So in my case I was using the text and math files, and then you need to specify the exact directory that you want to save your simulations. So in this case we are going to choose a directory. I'm going to use this directory here. And now you can set up the parameters for your simulation. So for example, we can disable spatial consistency, disable human blockage parameters, and we can select the scenario that we want. So for the sub-terahertz we used the indoor scenario here, and then you're allowed to use a maximum frequency of 150 gigahertz. If you use the UMI, you'll be capped to 100 gigahertz. So in this example, I can try to use 130. I can specify the bandwidth, which we're using 80 megahertz. I can specify line of sight or non-line of sight. I can use the separation distance. So if I want to fix to a distance of, let's say, 20, I could use lower bound and upper bound of 20, the TX power, the base station height, user terminal, number of RX locations, the pressure, humidity, temperature, polarization, where I use the copolarization. You can define the TX array type for your transmitting antenna or the RX. So I'm just going to use ULA in this example. And here, if you want to do, for example, massive MIMO, you can select the number of transmitting antennas and the number of receiving antennas. So here I put a 256 by 256. The antenna spacing 0.5. If you want to add more antenna elements, you could also use this option here, but in my simulation I just kept as one. You can also adjust the azimuth angle and the elevation angle. And after you have all the parameters ready, you just click Run. And you need to wait for some time until the simulations are ready. Okay, now the simulations are ready, so we can go on the directory, and we can see here we have the generated simulation parameters. So the plots, basically, as you can see here, we have the same plots that we discussed in our presentation. So this is for the directional PDP. You also have the omnidirectional PDP here. If you want to check the path loss, you also have the path loss plot. If you want to check the small scale PDP, you also have the small scale PDP, right? And if you want to check what were the simulated results, you can just open the notebook and you will have the simulation parameters that you did for this experiment run. So the same parameters that we have configured on the graphical user interface. If you want to check more details of the generated simulations, KPIs parameters, you have this other direct PDP info where you have the time delay, received power, the distance that you used. So you're able to capture all this information on this directional PDP, DPDP file. and there's other files here as well for the other parameters. So if you want to reuse those parameters in MATLAB or in text format using a Python script or whatever language you like, you can use as well. So basically this is the presentation for the new eSIM that we have used for this simulation. So thank you very much for watching this presentation.